everyone. I am Assistant Professor Urmi Shah from IT/ICT Department of LG Institute of Engineering and Technology. So let's start or let's resume with our sessions on pulse modulation technique. Up till now we have studied it regarding what is analog modulation and what is digital modulation. Now let's move ahead with the further topics of pulse modulation technique. Basically, in analog modulation technique, we all were focusing on the variation of parameters like amplitude, phase and frequency. So relating with those parameters, we have studied it amplitude modulation, phase modulation and frequency modulation. Now in the upcoming sessions, we are moving towards digital modulation technique, which is going to focus on one of the frequently or quite used technique, that is pulse code modulation technique, and moving further we will be seeing the delta modulation technique. So let's start or let's move ahead with the further topics of pulse modulation technique. This is basically unit 6 of our session, and in this session we are going to cover the following topics, that is pulse modulation classification, how there are different types of digital modulation technique, how it is classified into various blocks or various modulation schemes. So that we will learn in pulse modulation classification. Then moving further, again same way which we had in our analog modulation, that is amplitude variation, frequency variation and phase variation. In this section also, in digital modulation categories, we will have different types of variation with respect to amplitude, width and position of the signal. In this session, we are going to focus on pulse amplitude modulation technique, which is going to basically focus on PAM. PAM is nothing but pulse amplitude modulation scheme. Moving further, we will be learning about the waveforms of pulse amplitude modulation, and lastly we will look upon pulse amplitude modulation demodulation part. So these are the topics which we are going to cover in today's session. So let's start with this topic. So firstly, we need to classify what is pulse modulation. Basically, pulse modulation is classified in two categories, that is analog pulse modulation and digital pulse modulation. In analog pulse modulation, we are having the following three categories, that is pulse amplitude modulation, that is PAM. Then we have pulse width modulation, that is PWM. And lastly we have pulse position modulation, that is PPM. Similarly, again in digital pulse modulation scheme, we have the following classification, that is first one is the pulse code modulation, that is PCM, and secondly we have delta modulation, that is DM. Further upgradation in delta modulation is done in form of adaptive delta modulation, that we will be learning in the upcoming sessions. So up till now, we have seen the classification of pulse modulation. Following modulation, we are going to study in this session. So the first one is the advantages of pulse modulation. Why we are using pulse modulation? What are the advantages of pulse modulation? So basically, in pulse modulation, the transmitted power is no longer continuous as it is in continuous wave modulation, but actually it is in form of pulse. Its nature is pulse in form. So next point is vacant time between pulse occurrence filled by interleaving multiplexing pulse waveform of some other message that is stereo. So these are the advantages of pulse modulation. Following advantages will help us understand why pulse modulation is preferred. So now moving ahead, what is sampling theorem? Like why we need to have samples formed from the analog waveform. So basically, sampling theorem provides a mechanism for representing a continuous time signal by converting it into discrete sampled or discrete time signal and taking sufficient number of samples of signal so that original signal is represented in its sampled form completely. So basically, it can be stated as a band limited signal of finite energy with no frequency component higher than the message signal frequency, that is FM Hertz, that is completely described by the sampled values which are at uniform time interval, and that time interval is less or equal to 1 by 2 FM. That is the actual bandwidth. So Ts is our sampling period 1 upon 2 pi FM, and 2 FM is our bandwidth, which is the actual sampling bandwidth. Minimum bandwidth required such that analog signal can be converted into discrete sampled signal without any distortion or aliasing process. So this is what sampling theorem says. And actually, this sampling theorem can be represented as sampling frequency must be equal to or higher than 2fn. That is, fs is our sampling frequency. It should be greater than or equal to 2fm. 2fm is the minimum frequency range or minimum bandwidth required so that we can transmit our signal from analog to digital conversion and such that it can be attained without any distortion or aliasing process. Now basically a continuous time signal may be completely represented in samples form and it can be recovered back if fs is greater than or equal to 2fm. So here fs is our sampling frequency and fm is our maximum frequency component for message signal. So this is what actually sampling theorem means. The sampling theorem is a very important and very basic topic whenever we are dealing with analog and digital communication. So this topic you all must refer. It will be definitely there for your exams. So this is one of the important concepts whenever we are learning digital modulation scheme. Now moving ahead with the pulse amplitude modulation. What is basically PAM? Firstly, it is categorized under analog pulse communication. So amplitude over here is varied with respect to the instantaneous amplitude of message signal. So basically the amplitude of the pulse or amplitude of the carrier signal is varied with respect to the instantaneous amplitude of message signal available, and the width and position of pulses are kept constant. If it is pulse amplitude modulation, that means we are varying the amplitude. If it is pulse width modulation, that means we are varying the width. If it is pulse position modulation, that means we are varying the position of the signal. Whatever we are varying, the other two parameters will remain constant. Total we have three parameters, that is amplitude, width and position. If we are varying amplitude, width and position will remain constant. If I am varying width, amplitude and position will remain constant. If I am varying position, and amplitude and width will remain constant. So this is the logic which we are working or which we are applying in modulation scheme concepts. Now basically PAM, that is pulse amplitude modulation, could be a single polarity or double polarity. Now what is single and what is double polarity pulse amplitude modulation? Basically, in single polarity pulse amplitude modulation, a suitable fixed DC bias is added to the signal to ensure that all the pulses are positive. And in double polarity PAM, here in this pulses, both are negative and positive. So this way we can have variation in pulse amplitude modulation. Now as you can see over here, this is the waveform of pulse amplitude modulation. Firstly, we will have the modulating signal, then we will convert it into form of sampled signal, that is our discrete sampled signal. Then we will have natural PAM, that is naturally we are varying the amplitude of the signal. Then we will have flat top PAM. See, these are the two different processes of sampling, flat top sampling or natural sampling. In natural sampling, directly we will have samples based on the level of signal, while in flat top we will have with respect to the sampled values and the analog signal. So this way we can have the PAM, that is our pulse amplitude modulation signal. Depending on the type of sampling in PAM, we can have ideal sampling or we can have natural sampling, and thirdly we can have flat top PAM. So these are the three different types of sampling which can be achieved in pulse amplitude modulation. The advantage of these modulation is it can generate and it can detect a very easy modulation, as it is allowing multiplexing also. And the disadvantage of these modulation scheme is it is having large bandwidth. The bandwidth requirement for transmission of signal is quite larger. So we require a band pass filter whenever we are retrieving the original message signal or the transmitted message signal. So this is the drawback, but otherwise the advantage is it is having very easy detection. Now for a PAM signal, whenever it is produced with natural sampling, the sampled signal follows the waveform of input signal during the time that each sample is taken. Further, whenever a PAM signal is generated using pulse stream, which is called sampling signal, it will be then operated on an electronic switch or a chopper circuitry. Chopper circuitry will have discrete samples of your signal. It will produce the samples of analog message signal, and the switch is closed further for a duration of each pulse, in which it will allow the message signal or sampling time for a sampling time such that it can be a part of the output. Now the switch is open. Whenever you are opening the switch, at that time you will have a reminder of each sampling signal or sampling period, which will make the output 0. That is known as natural PAM or natural pulse amplitude modulation. While what will happen here in the simplest form of PAM, you can visualize the output of an AND gate whose two inputs are message signal x of t and the pulses of sampling rate. Now over here, if you have a flat top sampling, a sample and hold circuit will be used to have discretized chopping and hold of signal, and then the amplitude of each pulse will be constant during the sampling time. Flat top sampling produces pulses whose amplitude remain fixed during the sampling time, and the amplitude value of the pulse depends on the amplitude of the input signal of time, which is equal to sampling time. Here a aperture effect can be seen, which is again a type of TAM equalizer effect which will be generated at the receiver end. Over there we can use equalizer to have equalization for the transmitted signal. So basically we require a minimum transmission bandwidth of 2 FM, that is Fs is equal to or greater than equal to 2 FM. Further, the bandwidth which we have used for pulse amplitude modulation will be ranging from 1 by 2 tau to Fm. Tau is basically our sampling time. So this way sampling process occurs in PAM. Further, what are the transmission and drawbacks of pulse amplitude modulation and what is the demodulation process of PAM we will be discussing in the upcoming sessions. Following are the reference books for the topics which we have referred in today's session. Thank you very much for watching this session. Thank you.